Hello, my name is Oskari Kerppo, and today I'm here representing Quanscient and presenting the use case demonstration we did together with VTT on the VTT quantum computer. Quanscient focuses on multi-physics simulations. So multi-physics is when you are simultaneously modeling different coupled physical phenomena. So examples would be, for example, fluids interacting with structures, perhaps wind interacting with a bridge, for example, or acoustics, so a vibrating structure generating sound, or perhaps the thermal and electromagnetic properties of electric components. So here are some key numbers with Quanscient. We are founded in 2021, headquarters based in Tampere, and we have a very diverse workforce of around 40 employees. So what are some of the traditional bottlenecks in classical simulations? So it takes a long time to build simulations. And it is a very difficult problem to even model the actual physics behind the problem. And then it takes a lot of money to perform the simulations. You have to have hardware or some cloud resources, and it's typically very slow to from modeling your product until the product actually sees the market. So these are the things we are trying to make faster. And actually, with Quanscient also, this is our product. It is a cloud-based product where we can already speed up simulations significantly, so we can achieve large speedups and scale up physical simulations, and this can be seamlessly integrated in your design workflow. And this is what is available today. In the future, we are looking to go beyond what is possible with classical resources and actually make the impossible possible with quantum computing. So going to the demo with VTT quantum computer, we did a fluid dynamics simulation on the actual quantum computer. So here we have the classical validation of the model. So it is some aerosols spreading here through space, and this was validated on the CSC Lumi supercomputer. So it's the exact simulation, or the representing the ideal simulation. And then on the VTT quantum computer, this was, to the best of my knowledge, the first end-to-end execution of a repeated to the advection diffusion equation here, end-to-end on a quantum computer. And this underscores the huge potential quantum computing has in this field, addressing realistic computational fluid dynamics applications. Here on the bottom left, you can see the ideal simulation of this configuration. On the middle, you can see the actual result we got from the quantum computer, and we can see it very closely matches the expected outcome. So right now, the emphasis is on improving these higher level algorithms and practical quantum middleware engineering. So research gains from this collaboration, we gained quite a bit of information. So first of all, we had to adapt our quantum lattice Boltzmann method circuits for the quantum chip. So we chose the best subset of qubits for this simulation, taking into account the connectivity in the physical hardware. We utilized latest noise mitigation methods here. So we use dynamical decoupling to protect the states of the idle qubits during the execution. And we looked at the noise calibration, the calibration data directly that we got from VTT, and we sort of looked at this with some reference circuits to extend the noise model and actually build a classical noise mitigation model to correct some errors. And we saw quite a bit of improvement in the actual data once we corrected for the errors. Here, what we are looking forward to building in the future, we have, or this is a joint project with Airbus, where we are actually extending the quantum lattice Boltzmann method to 3 coupled phenomena. So here we have velocity, temperature, and stream function, which are simulated around an airfoil. So this actually represents a true multiphysics simulation. Here you're simulating 66,000 lattice points with 23 qubits. And this highlights sort of the potential that quantum computing has in these simulations. So this, as we heard in the previous presentation, these resources typically scale exponentially, and here the quantum advantage, one of the advantages is that we can scale these simulations up by adding the number of qubits. So in principle, adding a single qubit allows you to double the amount of lattice points you can represent, and then the algorithm at the same time only scales logarithmically. So the algorithm scales very favorably, while the size of the problem can be grown exponentially. Okay, so if you want to get in touch with us, here are our contact information, and please get in touch if you have any questions or got interested. Thank you.